All right, so we've been talking chapter 4, and last time we talked, and when you have ions, by the way, and where you find ions are basically in solution. So basically in solutions, that is where you basically find ions. They're floating around. That's pretty much where you find them sort of active and ready to go. And electrolytes are solutions that when they dissolve in water, will conduct electricity. And there's different types of electrolytes. There's strong electrolytes, weak electrolytes, and non-electrolytes. But it's actually the presence of those ions in the solution that helps it conduct electricity. Um, so let's talk about each of those maybe here. There we go. So for example, a strong electrolyte is something that will 100% break apart into ions, which means you have none of the whole unit still together. So if you took something like sodium chloride and dissolved it in water and you had a sodium chloride solution, in that sodium chloride solution, you will have 100% sodium ions and chloride ions floating around. You will have none of those guys in that actual solution. So if you made a solution of sodium chloride, all you have floating around are sodium ions, chloride ions, no sodium chloride units still together. Because it produces so much ions in that solution, it helps complete the circuit and all that, and it will conduct electricity really, really well. So this will conduct electricity really well. A very common experiment is you take like a light bulb and you hook some electrodes into it, you dunk it into the solution, light bulb will turn on very, very brightly. It will conduct electricity really, really well, and the light bulb will turn on really, really bright. So I'll go with a bright light bulb as that example. Now, if you have something that's a weak electrolyte, it will actually mainly stay together, but will produce some ions. Now, because it's able to produce some ions, it is still able to conduct electricity. So it still can conduct electricity. But we'll use the light bulb example. In the light bulb, if you did that, it would turn on, but it would look very, very dim, dying almost, but it will turn on a little bit. Now, an example of that, for example, if you took hydrofluoric acid, that is a weak electrolyte. And when you put it in solution, it will break apart into hydrogen ions and fluoride ions. But mainly what you would have in that solution is the HF unit still together. You'll have a little of these guys. So if you looked at sort of the test tube or beaker, you would have mainly the HF units in there, but you'll have a little bit of H plus and F minus kind of floating around in that solution. Because it still has some ions, it will still be able to conduct that electricity, but nowhere near the extent of like a strong electrolyte. You also will typically see these arrows that head in both directions when you talk about a weak electrolyte. And that means that this reaction is what is referred to as being reversible. And what happens is at some point, you will start to make products, which is going from reactants to products. Left to right is referred to as the forward direction. At some point, you'll make enough products that those guys will recombine and head back the other way, which is referred to as going in the reverse direction. So as you go this way, that is the forward direction. And again, as you make some products, it will then head in the opposite way, which is the reverse direction. It will eventually come to what's known as chemical equilibrium. And for you, that is also known as Chem 1B. That's all you talk about in Chem 1B. But eventually, the rate at which it goes back and forth will actually equal chemical equilibrium. Difference is happening at that point. The last type of electrolyte, which is really a non-electrolyte, will dissolve. But no ions are produced. So it will not conduct electricity. Non instead of no conduct, non-conduct electricity. So something like sugar, for example, right? Sugar will dissolve in water, and you'll get sugar that's dissolved. But sugar's made up of carbons, hydrogens, and oxygens, which means they're actually covalently bonded together. They share electrons. You don't make any ions when you do that, so it will not conduct electricity. That's also why water, just so we're clear, the water that comes out of your pipes when you take a shower is not pure water. Yes, they actually put ions in it to clean it, and you will electrocute yourself if you try to blow dry your hair in the shower. Yes, so don't do any of those stupid things. But they actually do put ions in there to kind of clean it. So that's why obviously normal water, right? We have to be careful with electronics because it will conduct electricity because they actually put ions in there to kind of clean it. Yeah. I don't recommend any electronic devices in your shower. I'm gonna say so. Unless it's made for it. I don't know. They have weird shower things now, right? With music and all that kind of stuff. So I'm gonna say take caution always when you're dealing with water. So just take caution. Water dangerous. Be careful. All right. Use at your own risk. Is that enough warnings for anybody listening? All right. All right. So here's the example of that light bulb. This is a non-electrolyte like pure water. Light bulb doesn't go on. Again, there's really no ions in there to help conduct electricity. A little bit of water with some sodium chloride dissolved in there. It's enough to get our light bulb again to conduct electricity really brightly. A dim or not a weak electrolyte would be, it would turn on again, but be very, very dim when you did that. All right. This, by the way, is what an ionic compound looks like when it is not dissolved. All the ions come together. And why is the positive ion smaller than the negative one? How do you become positive? You lose electrons, which means you shrink, right? Your electron field kind of cloud gets smaller. Negative guys gain electrons, which means they gain electrons in their sort of cloud and they become larger. So that's why it comes, right? You throw some water in there, you stir it, helps it all dissolve when you start stirring it and stuff like that. All right, one last thing here. When we talk about putting these ions together, a positive ion and a negative ion, the overall charge when you write the chemical formula for it should always equal 0. So you always want to have the simplest way to get to 0. So when we take something like a sodium ion, which is +1, and a chloride ion, and we put it together, +1 and -1 has no charge. So we write the formula for an ionic compound as sodium chloride. The formula for an ionic compound should never have a charge in it, but it is made up of two things that do have charges. It's made up of a cation, which is positively charged, and an anion, which is negatively charged. So if we took our barium here, which is +2, and our oxygen, which is -2, again, we just need one of each of those, and that will give us BaO, which is the proper formula for barium oxide. Again, the combination of those two things have no charge, but again, it's made up of two things that are charged. And that always happens when you take a metal and a non-metal together to make an ionic compound. It is always made up of something that has charges, but the overall charge should always equal 0. If things do not have the same charge, like aluminum and sulfide, you want to think about the common number. And the common number can be found very easily by just multiplying those two numbers together. 3 times 2 is 6. And that is the simplest way to get it to 0. So all you have to remember is I got one aluminum with +3, which means to get this guy to 6, I need 2 of them. To get the sulfide here to 6, I need 3 of them. And then you just write how many you put there. So that's 1, 2, 1, 2, 3. And you get the proper formula. Sometimes people are taught to do the switcheroo. Doesn't work 100% of the time. So if you want it like 93% of the time working, you could just blindly switch the charges, but it will not work most of the time or all the time. So it's a good idea just to kind of think about it like that to balance out the charge. Same thing with our potassium and our phosphide. Again, 3 times 1 is 3. So really I need more of this guy and a grand total of 3 of them. That gives me a +3 here to balance out my -3 on this side. And I have 3 potassium. So I write the number on the bottom. I have 1 phosphorus, and that will give me my proper formula. Any question about there? Okay, we're going to talk about here chapter 11. because we kind of skipped it for a bit, so we should go over it. So in this chapter, we're going to talk about modern atomic theory. We're really going to talk about electrons, sort of what happens as they move from one energy level to the next, and we'll talk about electron configuration and a little bit of periodic trends to officially go over it, even though I think we sort of covered it earlier. So as we talked about with Rutherford, he basically described an atom as having this large sort of positive core, which is known as the nucleus. And we have our negatively charged electrons flying around. So remember, we have this large positive charge here. That's from our protons being present. We have our neutrons that have no charge. And out in that empty space in the atom, we have our electrons, again, moving around pretty randomly about the nucleus. There's an attraction between the electrons, which are negatively charged, and the nucleus, which is positively charged overall because of the protons. As we also talked about, really the nucleus is a very small sort of size compared to the rest of the atom where the electrons are traveling. So in this chapter, we're really going to talk about sort of where electrons are sort of found in the atom. But before we get there, a lot of the work done to sort of understand this has a lot to do with radiation and waves. So one earliest sort of work was done by Planck. He heated a bunch of solids, and he noticed that energy coming off would only really come off in whole number multiples, which is sometimes referred to as a quanta of energy. And that's basically the energy can be released in these certain definite amounts. So in relationships to what we're talking about is the idea of, for example, electrons on different energy levels. And if an electron was to gain energy and end up on a higher energy level, if those lines represent energy levels, it would gain enough energy to make that transition. And the same idea is as they lose electron or lose energy, the electrons would lose enough energy to make it back down to another energy level. So if you had a bunch of energy levels, for example, and you had electrons sort of transitioning, the idea here, quantized energy, is it will gain enough to be fully on one level or the other. It will never sort of find itself between energy levels, just kind of hanging out, bless you, between them. So they're either gain or lose energy enough to fully make it from one energy level to the next. And that's what the idea of quantized energy is. And we'll see a picture of it later, but it's sort of also sometimes referred to kind of like a staircase sort of idea. When you walk upstairs, you have enough energy to get to this stair, this stair, this stair. Usually when you walk upstairs, don't stop halfway between and go, I don't really got enough energy to kind of get between there because you're going to fall. And that's sort of how electrons transition. They, again, will either gain enough energy to fully transition upwards to one energy level, two energy levels, whatever it may be, and transition downward the same. And just like when somebody walks stairs, somebody could do one stair at a time, maybe somebody could do two stairs at a time and so forth. And they have enough energy to do those sort of transitions. And that's where the idea there, again, of quantized energy. So we'll never find an electron usually just kind of between energy levels. They'll either be on a certain energy level or another energy level, but never sort of between. So to understand this idea of Planck, we have to know a little bit about radiation. Radiation is basically the emission or transmission of energy through space in the form of waves. So basically energy is basically going to be carried out through space in the form of these waves. And the idea of the law of conservation of energy is that we don't lose nor create any energy. So in order for example, electrons to transition upwards, they do need to gain a certain amount of energy. And when they do want to kind of come back down to a lower state of energy, those electrons has to give off a certain amount of energy. And again, that energy is usually given off in the form of a wave. So let's talk a little bit about waves here. A wave can be thought of as a disturbing disturbance by which energy is transmitted. The speed of the wave does depend on sort of what it's traveling in, and there's our bird enjoying his stay at the beach, and the wave is actually passing through him as it goes up and down. Speaking of which, we know waves carry energy, as we'll talk about, right? If you ever been at the beach or in the water, you got hit by a wave, you know it carries a certain amount of energy as it clobbers you down. So energy is going to be transmitted through space. And the wavelength is the distance really between any peak or trough, so kind of between two peaks would be lambda, and the wavelength, or even two troughs. In terms of wavelength, I would say very commonly meters, centimeters, and nanometers are very common units. Probably the big two on wavelength is meters and nanometers. Nano is like 10 to the -9, so that's a very conversion that you use a lot. Frequency, which is new, is the number of waves that pass through a particular point in a given second. It usually has units of a hertz or a reciprocal second, and they are kind of a one-to-one relationship. So a hertz is basically the same thing as a reciprocal second. So very common frequency is given, like I said, in hertz. Like when you tune your radio to 95.5 megahertz is the frequency. And again, if you do see a hertz, it's the same as a reciprocal second. The amplitude is really from the midpoint of the peak there to the base there is the amplitude of a wave. You could calculate the speed of a wave by taking the wavelength times the frequency. And that's because we just look at units for, say, the speed of the wave, wavelengths in meters. Basically frequency is 1/second, so you get some type of speed of like meters per second when you kind of multiply those guys together. And that's a very common sort of unit of speed of a particular wave. Any questions on those there? There we go. Now, light behaves like electromagnetic radiation, which again is that emission of energy in the form of these waves. They do have sometimes electromagnetic radiation does have properties that are very characteristic of particles, and sometimes they do have it's very consistent of waves. So it's oftentimes when you talk about this type of stuff here, people mention like the dual nature of light. It could have a wave-like function and also a particle-like function. And particles can have wave-like functions and act as particles. So there's sort of this dual nature, and then later on, they'll sort of use waves to describe what's happening with something, for example, like an electron. And they both can have sort of particles and wave-like function. Both of these things, electrons included, which is what we're talking about here. So one can think of basically a beam of light traveling through space as a tiny packet of energy, which are called photons. And this is sort of the idea as, for example, an electron gets sort of promoted up to a higher energy level. These are energy levels. Electrons do want to always sort of be in a lower state of energy. So as it sort of comes back down, it will give off that energy again in the form of a photon of light. Now, depending on the wavelength of that photon of light, it may be something where you can visibly see it like a color if it falls in the visible part of the spectrum. If it falls maybe outside of that, and they say the infrared part, you may feel heat coming off. You've all sort of done this maybe in a lot of cases. I don't know if you ever boiled water and it maybe overboiled. When the water hits the flame changes. If you're boiling with some type of flame, it'll change color, and that's really the like sodium ions, basically electrons being excited, and you'll see that sort of about as those guys get a little excited and they release back down, and you see the color. We also see this as sort of the idea behind like fireworks as well. When you launch off fireworks, they explode, provides a lot of energy, excites all the electrons and those elements that are inside the fireworks. As they relax back down, they give off energy in the visible part of the spectrum, and we see colors like purples and greens and all that kind of stuff as they sort of explode. Now, there is a relationship between sort of the wavelength and energy. So if we have a longer wavelength, something like this, where it's just kind of moseying through space, which is much longer wavelength, it is a lower energy and also a lower frequency. And that's different than when we have a wave that has a much shorter wavelength. And with a wave that has a much shorter wavelength, we have a higher frequency. It occurs a lot more often, and that's usually associated with higher energy. So speaking of sort of like firework example, or where we see colors, even within colors, as we will see, there is a difference between energy between, say, red and violet, for example. Violet actually being more higher in energy than the red color that you would see. So there's a lot of energy associated with the wavelengths of those waves that are coming out. And again, we could think of these waves as having wave-like function, and also can be thought of as like a stream of particles basically moving through, and these are packets of energy. And there you can see our red color, much longer wavelength, versus our bluish color has a shorter wavelength. So this guy here should be higher in energy. And that should be a little bit lower in energy because of this color. Now, what does that have to do with maybe electrons transitioning? By the color that you maybe see coming off, you can make an assumption as to how many energy levels, for example, an electron may be transferred. So if you had an electron and it transferred from way up here all the way down, say 4 energy levels, that would be a lot more energy, and maybe you see a color closer to the blue. If you saw like an electron start at the second energy level and just drop to the first energy, that's not as much energy. So maybe that would give off more of a red type color, as it's not that much energy coming off. So, based on the color, for example, that you see, I could also make sort of an assumption as to how far perhaps those electrons traveled to release that. By the way, when they do go to lower energy, that is an exothermic process for the atom. It has to release that energy that the electron is losing. And just like when they kind of go to a higher energy level, the electrons, that's an endothermic process for the atom, as it has to gain that energy to allow the electrons to go up to a. This would be obviously giving off that in an exothermic type of process. The way the atom would in an endothermic process. Electromagnetic waves is the speed at which they travel, and they travel at the speed of light, which is 3 times 10 to the 8 meters per second. So that's a number that I'm sure they're going to want you to know as you continue your travels here in chemistry. That's roughly about 186,000 miles per second, which is pretty fast, I think. And speed of light is a constant. So that is something that you sort of always have available to you if you need it, is that 3 times 10 to the 8 meters per second. For electromagnetic waves, we could kind of use this equation, which is C is equal to the wavelength times the frequency. That again is going to give us meters per second if we use it just like that. We could also rearrange this. And if we know the frequency, we could divide the speed of the light by the frequency, and that will give us our wavelength in meters. And if we know the wavelength, we could find the frequency by doing really the same calculation. And that will give us our frequency in reciprocal seconds. So those are 3 ways that this equation is sort of rearranged. And oftentimes you can't solve for any of those things that are found in that particular equation. Any questions on that there? Yeah. Say it again. It's not really, there's not too much of a difference between that and the previous formula. This is the one most people will use because usually we're talking about electromagnetic radiation, which will equal the speed of light. So, no. Other questions? So definitely, there's a one that looks just like that, but this is usually the one that you would use in this situation here, the one that's equal to basically the speed of light. Other questions? So why don't we try one here? What is the frequency for a wave with a wavelength of 4.68 times 10 to the minus 7 meters? Okay, so let's take a look. So we're looking for the frequency. We have the wavelength. So we can use our C is equal to our wavelength times our frequency. Here, the wavelength is 4.68 times 10 to the minus 7 meters. Again, it is in meters, which is what we want because C is, I'm going to make a correction because here they actually would like you to learn, I think, 2.998 times 10 to the 8 meters per second, which is pretty close to 3 times 10 to the 8, but I believe that's the number they actually would like you to use for speed of light here. So I guess we'll use that number. And again, the wavelength does need to be in meters, is a so correctly. So we'll go into this and solve for our frequency, which is our speed of light divided by our wavelength. So 2.998 times 10 to the 8 meters per second. 4.68 times 10 to the minus 7 meters. The meters cancel, and that's going to leave us reciprocal seconds left over. Want to make sure you use your exponent button there, and you're going to look at something like 6.41 times 10 to the 14. Once again, the units will be 1 over seconds, or you could write reciprocal seconds kind of like that if you like. Any questions on that one? All right, so why don't you try this one? What is the wavelength in nanometers for a wave with a frequency of 5.6 times 10 to the 14th? Just a reminder, nano, I believe 10 to the minus 9. Okay, so once again, good news is kind of the same formula. C is equal to wavelength times frequency. In this case here, we do have the frequency, which is 5.6 times 10 to the 14 hertz. Remember that 1 hertz is the same as a reciprocal second, which means that is 5.6 times 10 to the 14 reciprocal second. For the wavelength, and once again, C is a constant, 2.998 times 10 to the 8 meters per second. So solving for our wavelength, which would be C divided by frequency, putting in our numbers here. Again, the seconds will cancel. That's in this case. And give us here 5.35 times 10 the minus 7 meters. We're looking for nanometers. A reminder that 1 nanometer would equal 10 to the minus 9 meters. We'll take our answer here in meters and do our conversion to nanometers. Remember that is 1 times 10 to the minus 9. And I'll get you something like 535 nanometers here. Questions on that calculation there. So we can use C is equal to the wavelength times frequency as long as we know one of them. We can calculate either the wavelength of that wave of light coming off or the frequency of it as well. So when we do have these electrons transitioning, like I said before, and energy is coming off in the form of these waves and these photons of light, they may fall somewhere on what is referred to as the electromagnetic spectrum here. And this is the electromagnetic spectrum. And when we look at it, we have wavelength up on top. So what we have going on over here is this is a longer wavelength. And as we've talked about, with that longer wavelength, that's going to have a lower frequency and a lower energy. as opposed to over here, which is 10 to the minus 12, which is a much smaller wavelength, which will have a higher frequency and a higher energy. So when we look down here at this end, we have things like the radio waves, which is not too bad. We listen to it in the car. As we move to the left here, we then have microwaves, which has a lot more energy and has enough energy, for example, to move water molecules really fast. So you can get your pizza in like 3 minutes when you heat it up in the microwave. Next to that is infrared, which is a little bit more energy. And that is sort of the area where you feel heat coming off of things in that infrared sort of spectrum. Then we have really the visible part of the spectrum, which is a little bit higher in energy. And the visible part of the spectrum is where we see colors, like our Roy G. Biv, right? Red, orange, yellow, green, blue, over there, blue, indigo, and violet. And we could also see that in terms of the colors, like I mentioned before, there is a difference in energy. Here, about 700 nanometers or so, that's going to give us our red, which is lower in energy because it has a longer wavelength, and about 400 nanometers, which is our bluish color here, which is going to be higher in energy. So usually the visible part of spectrum is, like I said before, where we see colors. So as in the case, like I said, of fireworks, or even like that water hitting the flame, or even like the flame test that we did way back when, experiment 16. Those are all exciting those electrons. And as those electrons come to a lower energy state, they give off that energy. And if it comes in this sort of visible part of the spectrum, that is where we see color coming off of it. Next to that is ultraviolet or UV, a little bit more energy as well. And that's why we wear sunblock, right? So we don't get too burnt out there from the rays. X-rays, more energy. Why they throw a lead vest on you and leave the room right when they shoot the X-ray. And lastly, gamma rays is just pure radiation. It's basically radioactive rays that have no charge, similar to neutrons, but really just pure energy. So as we go on this picture, kind of from right to left, we're increasing in energy. You do need to know these, the electromagnetic spectrum. You need to know the sense of, for example, putting things in order from like lowest energy to highest, or longer wavelength to shorter wavelength. Lower frequency to higher frequency. So you don't necessarily have to know exactly where all the numbers are for this class, but you do need to be able to kind of put those guys in order. That also includes the colors there in the visible part of the spectrum. So the red, orange, yellow, green, blue, indigo, violet. You need to be able to kind of put those in order the same sort of way: energy, wavelength, frequency. Any questions on any of that there? Now, as we've been talking about, atoms and molecules could emit or absorb energy in these discrete sort of bundles of energy. They're sometimes referred to. And again, that's our quantum of energy. And really, you can think of it, as I mentioned earlier, that it's the idea that these electrons will either gain enough energy or lose enough energy to, again, fully transition from one energy level to the next. And it may be multiple energy levels. It may transition from, it may be less energy levels as well. But they will gain nonetheless enough energy to make the full sort of transition. You could actually calculate the amount of energy by using this formula here. This is the energy is equal to H times the frequency. H is Planck's constant, and that is 6.63 times 10 to the minus 34 joules times seconds. Joules is the unit of energy. Seconds obviously is time. And if you think about sort of that equation and the one that we saw earlier, which is our C is equal to our wavelength times our frequency. And if I solve for my frequency, would be C divided by wavelength. I could actually substitute that into here, and you'll sometimes see this equation as HC divided by the wavelength. So the energy is equal to hc divided by the wavelength, or the energy is equal to h times the frequency. What that means is, frankly, if you know one of those two things, either you know the frequency, the light coming off, or you know the wavelength of the light coming off, you could calculate the energy associated with that photon by using these formulas, as h is a constant and also c is a constant as well. Any questions on that? Once again, here, wavelength does need to be in meters for everything to properly cancel out. So why don't we try one here? What is the energy associated with a wave that has a wavelength of 465 nanometers? So give it a go, see what you come up with here. Okay, so let's take a look. We are looking for our energy. In this case, we have a wavelength of 465 nanometers. So we do have our energy is equal to h times our frequency, which once again also equals hc divided by the wavelength. So we would want to use sort of this version of it, as c over the wavelength equals the frequency, since that's all we have is really our wavelength in this case. We do have to convert it to meters. So we'll take our 465 nanometers, again, 1 nanometer, 10 to the minus 9 meters. So that's going to get us there, 465 times 10 to the minus 9. Going to give us 4.65 times 10 to the minus 7 meters. The reason we need to do that, H, I'll use 6.63 times 10 to the minus 34 joules times seconds. Sometimes people might use 6.626, but we'll use this one. C, we'll use a 2.998 times 10 to the 8 meters per second. Once again, it does need to be in meters because of the speed of correctly. Putting this in, we'll take our 6.63 times 10 to the minus 34 joules times seconds, our 2.998 times 10 to the 8 meters per second, all divided by our wavelength, which has been converted into meters, so everything cancels. Little canceling action there. Seconds will also cancel. That's going to leave us just joules. So 6.63 minus 34 times 2.998 to the 8 divided by our weight. 4.27 looks like, times 10 to the minus 19 joules here in this case. Any questions on that calculation there? So once again, all you need is the wavelength or the frequency, and you can calculate the energy associated with that photon of light. Any questions on that calculation? All right, one last one here. What is the energy associated with a wave that has a frequency of 2.87 times 10 to the 14 reciprocal seconds? Equals h times the frequency. In this case, we were given the frequency. And we're looking for the energy. So we really do have everything we need. Planck, again, is a constant. 6.63 times 10 to the minus 34 joules times seconds. So just plugging it in here. Times our frequency here, 2.87 times 10 to the 14 reciprocal seconds. So that's 1 over seconds, which means those guys will cancel out. And we'll end up with, making sure again, exponent button here, 1.90. Question on that calculation there. All right, so using these formulas, very common, again, to calculate energy, wavelength, frequency, obviously as well, if you have the energy associated with a photon of light, you could use these equations to calculate the frequency or wavelength of that photon that came off. Any questions on that calculation?